Hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome all members into our discussion for today, and we're going to look at the concept of the mean value theorem. Basically, this is going to be a review of these specific concepts which we have particularly looked at in conjunction with the Rolle's theorem. And we said these are going to assist us in trying to describe various, of course, a range of values which we are going to see between the closed intervals of a and b for a continuous function, and the, of course, aspect of these specific intervals for a differentiable function. Now, in this case, I've chosen a particular point which is going to be given along this x-axis in terms of this point P. Now, in this case, I've just going to monitor the relationship between this specific point and this line of a and b, which is going to be part of this specific function that I've written as y is equals fx. Now, that's going to be giving us the relationship between a point between these particular intervals of a and b. And this is going to be, of course, generally be described using this specific formula. Now, we are required to show that by the mean value theorem, this is going to be the relationship between this specific, of course, point which I've chosen for x, and of course the function which we're going to consider given on the board. Now, in this case, I've just given these two specific points, and in our last discussion we had mentioned that basically this mean value theorem is going to be assisting us trying to define some of the concepts which we came across, especially for Rolle's theorem, whereby we said that if we have a function which is can be given in terms of y is equivalent to f of x given as such, this function is going to be of course defined as a differentiable function and continuous at some of the intervals, for instance, which I've just given on the board. Now, by the mean value theorem, this statement we had said that for a function of x given as such that is continuous at each point of these closed intervals of a and b, and this specific function, if it's differentiable at the, of course, open intervals or closed intervals of a and b, then there's at least one number which is going to be a c between these particular intervals, whereby we're going to see that the first derivative of this specific, of course, function at b is going to be given in terms of the derivative of f of a, f of b given as such, and over b minus a given as such. So basically, this is going to be a derivative of this specific function at this point, and we had just explained that this basically is going to be a point which is going to, or a function which is going to be parallel to this specific, of course, line of a and b, and that's according to the mean value theorem. Now, in that case, we had considered a specific, of course, tangential component of this particular function, which was described as such. And in our previous discussion, we did an analysis of this specific function and tried to find out its, of course, derivative, which we came up with this specific formula. Now, the relationship between this specific, of course, function or relationship with Rolle's theorem, we said that for Rolle's theorem, the condition which we have set for this specific function is going to be the same, only that for the first derivative of this particular function, the first derivative given as f prime of c is going to be equivalent to 0. So this basically gave us the concept of a maximum and a minimum, whereby we see that this specific function then therefore is going to be defined by these extreme points of a maximum and a minimum given as such. And these extreme points are going to be defined by these specific functions, whereby we're going to see that particularly for this particular point, the f prime of this specific function is going to be a 0, whereby we're going to have, if we say that this is going to be a function defined by that particular point, then therefore we're going to see that the tangential component of this specific function are going to be having of course, the first derivative given in terms of a 0. So for instance, if this was a point c and another one d, so the component still is going to be the same, where we're going to have the f prime of a d still equivalent to 0. So the relationship between this specific aspect of Rolle's theorem and the mean value theorem is that definition of this specific function. And we're going to see that from this specific illustration, then therefore we can have a general way of trying to show that basically for the mean value theorem, we can have this relationship given below this particular illustration to be true. So I'm going to consider just having this specific point which I've just written for x, and I'm going to monitor the relationship between this specific x and the other 2 points which I've given for the intervals of a and b. So we can have the gradient of this particular point for a and b given in this specific form, whereby we say that the gradient basically is going to be given as a change in x-axis, change in y-axis over a change in x-axis, which we can give in terms of, let's have AB as our function, of course, and try to see what we're going to get as a gradient of that one. And this is going to be giving us FB, which is going to be FB minus FA, which is a change in F. This is going to be FB minus FA divided by B minus A for x. So we're going to have B minus A for the change in x. And this basically is going to be giving us the gradient of this specific function. Now, if we try to look at this one, if this is going to be a straight line, and therefore we are going to have AR being a section of this specific line, and therefore we're going to have the specific gradient of AR given in terms, let's just have that notation for that specific case. We're going to have the gradient of AR given in terms of, so we're going to have these specific coordinates which we're going to give in terms of x and y, but I can have this one given in terms of x and the function, the f of x given as such. So we can define the gradient of this one given in terms of the change in x, fx minus a all over. So this is going to be basically f of a for the y, of course, a part of the coordinates divided by x minus this specific value of a. So this is going to be x minus a. So in a sense, we're going to see that if this is going to be a straight line between a and b, and AR is a component of a, b, then therefore the gradient of those two lines are going to be, or that specific continuation is going to be the same, implying that the gradient of this one is equivalent to the gradient of this. Therefore, it's in order for us to have an equation of the form this specific nature, whereby we're going to equate this specific aspect of the gradient, and we shall have a continuation of this specific description, whereby we're going to have this one defined in terms of the function. This is going to be the gradient of this one, can be defined as fx minus fa all over x minus a, which is going to be similar to this gradient, is equivalent to this specific relationship over fb minus fa all over b minus a given as such. So in this case, we're going to consider this specific, of course, relationship which I've just given on the board, whereby we're going to see that we can have a rearrangement of this specific formula for us to have the relationship over fx minus fa is equivalent to fb minus fa for this one, and then this is going to be all over b minus a. But we're going to have this numerator as a factor, and therefore we can divide, we can multiply on both sides by this specific numerator for us to remain with fx minus fa. And this is going to be giving us x minus a given as that. So in this case, this is going to be giving us the relationship of this specific, of course, points which we have particularly defined, which is going to be similar to this specific relationship which. So basically, this is going to be holding for the mean value theorem. Evaluations in trying to, of course, monitor whether this is going to be the case for various range of Rolle's theorem and the application areas, which of course are going to be pertaining the same topic. So in that case, kindly check our description boxes for various links of other videos. Engage us in the comment section and also ring that notification bell for various updates on different discussion in mathematics and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.